Okay, so I'm the first presenter. I'm going to talk about sort of a cute little trick that we're going to use in seismic interferometry. And this was work with Kaoru Sawasaki. He was a postdoc with us for a year. He now returned to Japan, where he works at the National Research Institute for Earth Science and Disaster Prevention, sort of the equivalent of the United States Geological Survey. And I want to take you back to topics we talked about in earlier years, which is seismic interferometry, where the key idea is that if you record noise at two sensors, they're labeled A and B here, and you have noise sources which are nicely distributed around your sensors, you get the Green's function, you get the waves that propagate between these two sensors. So you basically are turning one of those sensors into a source. And this requires that the sources are what is called equipartitioned. You must have sources with the same strength on average surrounding the receivers. But we also know that out of these sources, only a limited number of sources are really contributed to the Green's function reconstruction. Those are what are called stationary phase locations. They're indicated in blue, and the main idea is that the blue sources, they launch waves that first hit one receiver and then they propagate to another receiver. And of course, you must have waves that propagate between each receivers because there's no magic in geophysics. You can never, by data processing, extract or reconstruct a wave that doesn't exist in reality. So out of all these sources, only a limited number of sources contribute. And we're going to use that later. Now this whole concept falls apart if we only have, let's say, one noise source. And this often is the case. We make an isolated noise source. Case in point, for example, is drill bit noise, where you make an isolated noise source. And it's obvious that you're not going to get the waves that propagate between these two sensors because cross-correlation takes the difference of the arrival time arriving at these two sensors, and the difference in the arrival times of the waves traveling from the source S to these two receivers is always going to be less than the travel time of the waves to propagate between these two receivers. So with isolated noise sources, in general, you get biased estimate of your Green's functions, you get biased estimate of your arrival times. So the question we asked ourselves is, well, can we fix this? And if we have an isolated noise source and just a limited number of sensors, can we still find the velocity? And the whole concept is to use a rotating array. What if we could use two sensors and we could put them on a rotating array? That would sort of mimic the situation that we had earlier of sources all around us. And because out of all these two pairs of receivers, the blue ones are stationary phase locations, because for these blue pairs of receivers, the waves that are emanated by the source first hit one receiver and then they hit another receiver. So in principle, if we would have a system where we had two sensors mounted on a rotating system, we could do with a single noise source. That wouldn't be very practical, of course, but you use this already. Because if there's, for example, there's a plane flying through the sky and you don't know where the plane is and you want to find out where it is, did you notice that the best way to find is to rotate your head a little bit? Or maybe I'm the only one who does it. If you see me do these, I'm just trying to find a noise source. This works really well, actually. Now, of course, there you're also looking at amplitude difference, but we have these sensors, by the size of our heads that are directional, so it's more complicated. But this is the main concept that we're going to use. So how we're going to do that in practice without having a rotating array, because obviously we're not going to mount seismometers on rotating beams that we're going to rotate in the landscape. So let's look at the case where we have one noise source, we have one plane wave propagating, it propagates in the direction n hat. It has a certain source time function, s omega in the frequency domain. And we are going to compute a normalized cross-correlation, that's what you see in the top expression, and that gives you just the exponential, which has the wave number in there, that's of course the quantity that we ultimately want to know. It has the direction of propagation and hat in there, and it has that interstation vector R2 that connects these two receivers with each other. Now, in general, of course, here we cannot do interferometry in a useful way because we get something that looks like a plane wave, but of course that the direction of propagation and hat and the interstation vector are not aligned. So of course this is going to give us a biased estimate of the wave number. So this in itself is not going to do much good. But what if we had three receivers? If we had three receivers, we have two interstation vectors, I denote them with R2 and R3. Can we do it now? And the answer is yes, we can, because out of those two interstation vectors, R2 and R3, I can build any vector that points with any direction in the horizontal plane. So we define now another unit vector, P hat, that makes an angle. I denoted it phi with some arbitrary direction, and we can express that unit vector P hat into these two interstation vectors R2 and R3. And so for any angle phi, we can find those coefficients A and B that tell us on how we should combine those two interstation vectors to give us a vector that's oriented in an arbitrary direction. And then to make this equation dimensionally correct, we put an R0, that's an arbitrary length on the left-hand side. We typically take some average of the interstation distances for R0. So how can we use this in interferometry? Well, it's actually a very simple trick. You take these normalized cross correlations, we have them on the left, and each of these normalized cross correlations looks like a plane wave. That gives us a plane wave in the middle expression on the right-hand side. And then we use that identity at the top where we express our two interstation vectors into a vector with an arbitrary direction. And now we can find that if we take these normalized cross correlations, we raise them to those powers A and B, and those are numbers that we know. We now get, on the right-hand side, you get a plane wave that propagates over a distance R0 times P hat. So this is like a simple data processing trick where we take two receivers, or three receivers, I'm sorry, with two inter-receiver vectors, and we combine them into a new set of receivers that can have an arbitrary rotation. So this is a mathematical trick to mimic that idea of having two receivers that you rotate. Because at angle phi we could choose arbitrarily, and for every angle phi we know those coefficients A and B, and we can find this plane wave. So this is a numerical simulation to show you how this works. So here we have three receivers. I'll show you the geometry in just a second. We have one plane wave coming in with just random noise. We cross-correlate the noise between these two pairs of receivers. We compute the normalized cross-correlations. We raise them to these powers A's and B's. We do that for every angle phi, where phi just sweeps from 0 to 360 degrees. And then we Fourier transform through the time domain. And you can see these waves that propagate, and they have a very sinusoidally shaped arrival time. And if we sum them, that's when the principle of stationary phase kicks in, and you get the two waves that propagate over the distance R0 that we specified. And that's what you see in the bottom panel. So this trick really works to basically give us the waves that propagate with the right wave number. You get an unbiased estimate of the wave number from just three receivers. So this is a simple data processing trick to mimic the whole idea of just taking these two receivers and rotating them around. And you can also look at that whole game in the simulation that I just showed you was in the time domain. You can also look at it in the frequency domain. You take that integral over that angle phi that you have complete control over, and you get a Bessel function that contains the wave number that you want to get. And this is again a numerical simulation. Here you see the three stations in the top right. The red arrow gives you the direction of the noise that propagates through this array. We never use the cross correlation between station 2 and number 3. Theory predicts that you get, if you compute that in those cross correlations and you raise them to those powers A's and B's that are a function of the angle phi, you integrate over the angle phi, you get a Bessel function. And that's indeed what you see, because the curve that you see is actually a superposition of a red line and a black line. And this is very much, of course, like, you know, if you go back to the original paper of Aki in 1957, where he really started interferometry in seismology, he showed that you get a Bessel function if you compute these cross correlations. And here we mimic that with just having one noise source propagating in one direction. So this works, that's the good news. The bad news is it really works if you have sort of one noise source propagating, one noise wave train propagating in one direction. If you get multiple wave trains propagating in different directions, this breaks down. And that's what we're going to show here. Here you see here is a number of noise wave trains coming in over a swath of angles that's indicated by the arrows that you see in that circle in the top right. And you can see that for low wave numbers we reconstructed the Bessel function very well. And then for a certain, as the wave number increases, the whole theory falls apart. And the black curve, which is that reconstructed Bessel function, doesn't really follow the real vessel function anymore, which is an indication that the theory falls apart. We have a criterion, and you can find the derivation in the project review book for the wave numbers for which the theory falls apart. The criterion depends on the angle delta theta between these different noise wave trains that propagate between my array. For all the parameters that we have used, the region of validity is indicated by the blue arrow, and you can see that agrees pretty well with this numerical simulation. So this is a simple trick that one can use if you have 3 receivers, and of course if you have more receivers you would absolutely use that information, of course. To do interferometry if you have just an isolated noise source, and as I mentioned before, drill bit noise or localized traffic noise or some industrial noise, that could be a nice application of this. So I want to enter this picture. You know, I love this picture. This dog with the giant ears, and that's really the trick that we're using, right? The dog with the giant ears tries to locate where the noise comes from by rotating its head. Only the dog and I do that, apparently. And if there's any questions, I'd be happy to address these.